with reference to this particular blog post by Probabilistic World, I'm going to derive the second raw central moment of a probability distribution, which is essentially the variance of a probability distribution again. And to do this, we're going to reuse the fact that the first moment, central moment of a binomial distribution, is the number of trials times the probability of success, or NP. Now, the way we go and define variance is essentially you're taking the average of the square distance of your arbitrary and random variable with respect to your population mean, which is described by this thing. Now this x minus mu squared, we can basically expand inside this expectation operator to get x minus mu times x minus mu. Multiplying it using FOIL or the grid area method, you get x squared minus 2 mu x plus mu squared. But here's another key thing, in fact, from linear algebra, and you can check this. E of x is indeed a linear transformation, so it is both homogeneous. Well, it's both additive and homogeneous, or some other term like this, which basically means that if I multiply the random variable by any real number scalar or scalar that belongs to a field, I can factor it out. And if I'm adding it by a constant result, I basically get that same constant result out as a result as well. So if I apply e to x squared minus 2 mu x and plus mu squared, that becomes e of x squared minus e of 2 mu x plus e of mu squared. Now, do note that mu squared is a constant, so we can basically factor this outside, and this is the same as taking e of 1, which is just 1 by default virtue. We can also factor out the scalar 2 mu here to get minus 2 mu of ex. But note that e of 1 is 1, and e of x by definition is just mu. So this e of x becomes mu to be minus 2 mu squared. And so we get e of x squared, the second raw moment, minus 2 mu times mu plus mu squared equals this stuff. This cancels, and we get a single minus mu squared. So the variance is the same thing as the expectation of the x squared variable minus the expectation itself being squared, which is just a fancy way of describing averages in terms of probabilities. Okay, so we're going to end up plugging in NP over here to reuse our result, but just like with how we derive the first raw moment of the binomial distribution, or the average, we're going to go and define the probability distribution, use the binomial probability distribution, and we get this ugly discrete sum, and we're going to play the exact same steps we did for the other proof, which are the following. Note that at x equals 0, the expectation value at 0 is 0 itself, so we can ignore the 0th term and start counting at x equals 1. So therefore we only have n minus 1 terms remaining. Now rewrite the variable binomial coefficient in factorial form. This will be a substitution that we make. Then we make a recursive factorial cancellation in the top and bottom of the numerator and denominator of a fraction. Factor out your constant number of trials from the expression as well as the constant probability of success. And eventually, oh wait, there's a bit more. Add in the exponent an arbitrary 0 pair in the exponent n minus x. This is the exponent that goes over the probability of failure factor. Now, next, after that, rearrange the terms by distribution of negative sign and commutative addition to get a really nice term, and then make 2 careful changes of variables. This basically shows us very anally that you have n minus 1 terms left, if you're only ignoring the first term or the 0th term of the thing, and adjusting the indices appropriately. And for the coup de grace, assuming our events are disjoint, the sum of the entire probability sample space is just 1. So then e of x squared, the only thing we need to worry about, because the other stuff is just minus quantity np squared, we just have to look at this. So we get x squared, c of n, choose x, p to the x times 1 minus p to the n minus x. Follows a nice Bernoulli trial there. We can ignore counting at x equals 0, so you just get x equals 1 to n for n minus 1 terms in total. Now we're going to basically write the combination into its factorial definition as seen below here. Now what do I do next? I go and bring this up together nicely into the numerator and this nicely into the denominator. Oh, I believe I cancel 1x at the top and the bottom. See, 1x is gone from here to the x squared to become a single x here, and 1x is gone from x factorial to make it x minus 1 factorial. Then, as a result of that, let's see. I factored out here, from here, I factored out the n and the p in this particular step here, which leaves us with an n minus 1 factorial and the p to the x minus 1. We're decreasing digits that way. And then if you look at this entire garbage, sorry, this stuff and this stuff, that garbage is essentially c of n minus 1 choose x minus 1. But now I'm going to add in the sneaky 0 pair, which is just add plus 1 minus 1 in the exponent for the probability of failure. And then redistribute the terms over again. So now I can easily make this substitution of variables that n minus 1 equals m and x minus 1 equals j. If I add 1 to both sides, I get x equals j plus 1. So I end up with np times this. And now where I made an error go, I'm going to distribute, split the sum and distribute across j plus 1. So I get np times this finite sum from 0 to m of this stuff, which we know what that is. That's basically the expectation value itself. So that's going to be another np here. And then this is going to be added by np. The np has to distribute to this single one term here. And again, we get the combination and the two factors, the number of successful trials and the number of failed trials that you get for a Bernoulli experiment. But this sample space, naturally, if I add up all the disjoint events and the probability, that's going to be 1. So that's going to be np multiplied by 1 again. Hence, we just get this, np factored out by this stuff again, plus np times 1. Yeah, and this is just np, just by noticing out carefully again. So we're just going to get np. Do note, however, it's indexed with a different variable, m, though. So it's going to be np times np. But like I said before, earlier, if we ignore the first term, we only have n minus 1 terms left that we're dealing with. So this is where n minus 1 comes from, if you didn't want to do just some tedious algebra there. But then you get np times n minus 1 times p plus np. And now this is just this single term here, which is going to be subtracted by this. Do some algebra from there. Be very careful, you can easily make mistakes. And you're going to get np minus np squared. Factor that out. Boom. We get the result we wanted, that the variance of a binomial distribution is np times 1 minus p, where p is the probability of success and 1 minus p is the probability of failure for the random variable of your trial in question.